Welcome to the third lecture in the 6th week of our course, Analysis of a Complex Kind. Today we'll talk more about the radius of convergence of a power series and how to find this radius. So recall what we proved last class. Given a power series of this form, ak z minus z0 to the k, where the ak's are complex numbers, there exists a number r that's between 0 and infinity. And both 0 and infinity are allowable values for r, such that this series converges, absolutely, in fact, for all z's that are within r of the center c0s, and it diverges for all z's whose distance from z0 is bigger than r. So we proved the existence of this disk, in other words, centered at z0, and of radius uppercase r, such that whenever you pick a z inside, for that z, the series converges, and whenever you pick one on the outside, for that z, the series diverges. On the boundary, we had no conclusive answer. Either convergence or divergence could happen. But how do you find this r? We know it exists, but how do you find it? Here's the first idea on how to find such an r. If the sequence of quotients, ak divided by ak plus 1, has a limit, then this limit is the radius of convergence of the power series. This theorem, called the ratio test, does not say that necessarily the sequence of quotients of successive coefficients has a limit. It just says, if that sequence has a limit, then that limit is the radius of convergence of the power series. So let's look at some examples. By the way, infinity is an allowable limit. So if ak over ak plus 1 absolute value goes to infinity, as k goes to infinity, then the radius of convergence r of the power series is infinity. In other words, it converges for all z in the complex plane. Here are some examples. So this is the series of z to the k. So here we have ak is equal to 1 and z0 is equal to 0. Remember, in general, we're looking at series of the form ak z minus z0 to the k, where k goes from 0 to infinity. So if we're just looking at z to the k, then the z0 here is equal to 0, and the ak's are all equal to 1. So if I look at ak divided by the next one by ak plus 1, they're all equal to 1. So it's 1 over 1 that's equal to 1 in absolute value, and 1 as k goes to infinity remains 1, and so converges to 1. Therefore, by the previous theorem, the radius of convergence is 1. Here's another example. Here, these ak's are equal to k, and again, z0 is equal to 0. So now if I look at ak divided by the next one, ak plus 1, well, ak is k, and then ak plus 1 is k plus 1. So that sequence of quotients in absolute value converges to 1 as k goes to infinity. Therefore, the radius of convergence again for this series is also equal to 1. Here's another example. Z to the k divided by k factorial. So ak now is 1 over k factorial. So if I look at ak and divide it by the next one, ak plus 1, well, ak is 1 over k factorial, and I divide that by 1 over k plus 1 factorial. So I look at 1 over k factorial divided by 1 over k plus 1 factorial, that's ak plus 1. And so I multiply with the reciprocal and end up with k plus 1 factorial over k factorial. Well, k plus 1 factorial is equal to k plus 1 times k minus 1, and so forth, all the way down to 1. And k factorial, that's k times k minus 1, and so forth, all the way down to 1. And so all these terms cancel out, except for the k plus 1 term that's left. So k plus 1 factorial divided by k factorial is simply k plus 1, and as k goes to infinity, that goes to infinity. Therefore, in this case, the radius of convergence r is infinity. So this series converges for all z's in the complex plane. Let's look at another example. Z to the k divided by k to the k. So now ak is equal to 1 over k to the k. So again, ak divided by ak plus 1 is going to be 1 over k to the k divided by 1 over k plus 1 to the k plus 1. And again, I multiply with the reciprocal, and I get k plus 1 to the k plus 1 over k to the k. Now, this is a little bit less clear on how to find the limit. I can actually find the limit. I'm not going to show you how, but the ratio test is a little harder to apply here because this limit is not as obvious. So I'm going to show you how you could find this limit. You could write this as k plus 1 to the power k times 1 extra k plus 1 factor. That's the numerator, divided by k to the k. So I keep this 1 extra k plus 1. I'll just move this over to the side. So here's my k plus 1. And here I have k plus 1 to the k divided by k to the k. I'll write that as k plus 1 over k to the k. Well, here's again my k plus 1. I'll just keep that there. And k plus 1 divided by k, I could split that up into 1 plus 1 over k, and then raise that to the kth power. You may or may not have seen this in calculus, but this sequence, 1 plus 1 over k to the k, actually has a limit. And the limit of that is e. That's Euler's number e. So everything in pink goes to e as k goes to infinity. But k plus 1, the orange term, goes to infinity. Since the second term goes to e and not to 0, the infinity just wins, and the whole expression goes to infinity as k goes to infinity. And therefore, ak over ak plus 1 actually has a limit. The limit is infinity, and therefore the radius of convergence of this power series right here is infinity. But suppose you hadn't known how to find this limit, what would you have done? So this last example we just looked at, ak was 1 over k to the k, is actually easier to treat using the root test. And it goes as follows. Instead of looking at ak divided by the next coefficient ak plus 1, you simply look at the kth root of the kth coefficient ak, and again you take the absolute value. If that sequence has a limit as k goes to infinity, then the radius of convergence is 1 over that limit. We have to be a little careful. So what if this limit is equal to 0? If the limit is equal to 0, then we say the radius of convergence is infinity, and if the kth root of the ak's goes to infinity, then the radius of convergence is 0. So this is how this is supposed to be read. Let's look at some examples again. So here's that series that we had some trouble with using the ratio test. Z to the k divided by k to the k. So here the ak's were 1 over k to the k, and if I look at the kth root of ak, it's the kth root of 1 over k to the k, but that's just 1 over k. And as k goes to infinity, that goes to 0. Since that goes to 0, now for the root test, we have to take 1 over the limit. And if the limit is 0, that means that 1 over the limit is infinity. So in this case, the radius of convergence is infinity. We had seen that by actually finding the limit in the ratio test. Next, look at the series k times z to the k. So the ak's are equal to k, and if I take the kth root of ak, that's the kth root of k. And it turns out the kth root of k actually goes to 1 as k goes to infinity, and therefore the radius of convergence is 1. We saw this using the ratio test as well. So often it is the case that it's not just one test that works, you can use multiple tests. So both the ratio test and the root test worked in this case and gave us that the radius of convergence is 1. How about the series 2 to the k times z to the k? So here my ak's are 2 to the k. If I take the kth root of 2 to the k, that's just 2. And as k goes to infinity, the 2 doesn't really change, and so the limit is 2. The radius of convergence, therefore, is 1 over 2, which is 1/2. Now let's look at this example. The series minus 1 to the k divided by 2 to the k times z to the 2k. Let's write out a few terms of this series. When k is equal to 0, I just get everything to the power of 0, so that's 1. When k is equal to 1, I get minus 1 divided by 2, so minus 1 half times z to the 2k, so z squared. When k is equal to 2, I get plus 1/4 z to the 4th. When k is equal to 3, I get minus 1/8 times z to the 6th. When k is equal to 4, I get plus 1/16 z to the 8th, and so forth. So I only have even powers of z. All the odd powers aren't even there. I only have even powers of z, and those are alternating in sign. So what are my coefficients? Well, a2k, the even ones, are of the form minus 1 to the k over 2 to the k. So these are even coefficients because I have a 2k here. So this is my a2k, what I see right there, because the name of the coefficient goes by the power of z. Since the exponent of z is 2k, this must be the 2kth coefficient. This is how the coefficients are labeled. Whereas the odd coefficients, well, they're not there. They're all equal to 0. So a2k plus 1, they're all equal to 0. 2k plus 1 is always an odd number. So those are all equal to 0. So now I want to take the kth root of ak. But that seems to depend on whether I'm taking an even coefficient or an odd coefficient. So let's look at the 2kth root of a2k and the 2k plus first root of a2k plus 1. The 2kth root of a2k, so I need to take the 2kth root of the absolute value of minus 1 to the k over to the k. So I need to take the 2kth root of the absolute value of minus 1 to the k divided by 2 to the k. So the numerator is just 1. So I need to take the 2kth root of 1 over 2 to the k. So that equals 1 over 2 to the k divided by 2k. So that's 1 over 2 to the 1 half. So the 2kth root of a2k is 1 over 2 to the 1 half. And the 2k plus first root of a2k plus 1, well, that's equal to 0, because a2k plus 1 is equal to 0. And so if I look at the whole sequence, the kth root of ak, that needs to include the even and the odd coefficients. Well, for odd coefficients, I get all these zeros, and for even coefficients, I get all these 1 over 2, 1 over 2, 1 over 2. So the sequence bounces between these two numbers, but it never comes to a limit because it keeps bouncing back and forth between these two numbers. So the sequence does not have a limit. The sequence not having a limit means I cannot use the root test. Note, ak over ak plus 1 has no limit either, because again, if I have an even coefficient in the numerator, I'm going to have a 0 in the denominator, that's no good. And if I have an odd coefficient in the numerator, that's 0, divided by something non-zero, that's 0. So it bounces back between 0 and undefined, 0 and undefined. So that's not really good either. So neither the root test nor the ratio test work in this case. Yet, this is a power series, so it has to have a radius of convergence. How can we find it? Here's an idea. We looked at this before. If you replace z squared with w, then the z to the 2k becomes w to the k. And so now the series, as a series in W, a power series in W, looks like a perfectly reasonable series because this whole even odd thing is now gone. I can take the kth root of the coefficients of this new series, so these are the coefficients. The kth root of the absolute value of that is the kth root of 1 over 2 to the k, so it's just 1 half. As k goes to infinity, that remains 1 half, has a perfectly fine limit. And so the series in the W's converges for absolute value of W less than 1 over 1 half, which is 2. So the root test works for the series in W, and it converges for absolute value of W less than 2. But W is simply z squared. So if the series converges when I plug in the W less than 2, then it also converges when I plug in the z squared less than 2. It's the same series. So the original series therefore converges when the absolute value of z squared is less than 2, and that means the absolute value of z is less than root 2. So the radius of convergence for this series is actually root 2. But neither of my two formulas worked. There's another formula that would find this radius. And there is. It's called the Cauchy-Hadamard formula. The radius of convergence of the power series ak z minus z0 to the k equals 1 over the lim sup of the kth root of the absolute value of ak. And this formula always works. There's no if this exists. The lim sup always exists. And this always gives you the radius of convergence. Just many people are not so comfortable with the lim sup, and therefore this is a less quoted result. But this result always works. So if the root tests fail and the ratio test fails, you can always use the Cauchy-Hadamard criterion. It always works. Remember, the lim sup is just the greatest accumulation point of the sequence. We have calculated the kth root of the ak's. The kth root of the ak's was simply bouncing back and forth between 0 and 1 over 2, 0, 1 over 2, 0, 0, 1 over 2, and so forth. And the lim sup is the greatest possible limit of a subsequence, basically. If you pick this subsequence that consists of these 1 over square root of 2's, then the limit of that is 1 over square root of 2. So r is 1 over that, and that equals root 2. We will be using the lim sup again in this lecture series, and so if you're not really comfortable with the lim sup and don't want to catch up on that right now, that's all right. Now, what does all this have to do with analytic functions and complex analysis? Remember, we had the theorem that says the power series is analytic for all those z's that are in the disk of convergence of the power series. So that's nice. You can build analytic functions using power series. But more is true. Here's a really amazing theorem. Suppose you have a function f that's analytic in some set u, so here's my u, and suppose you can stick a disk in there somewhere. So, for example, this disk right here fits into u, and I'll call it center z0, and it has a radius r. Then, in this disk, f has a power series representation, ak z minus z0 to the k, as long as the z's are from this disk. And, moreover, these ak's can be calculated. So I can calculate this power series. The ak's are exactly the kth derivative of f at z0 divided by k factorial. This power series converges in some disk of convergence, and the radius of that disk is uppercase r. We can calculate it using the theorems from the previous pages, and the r that you're going to get is at least the radius little r of the disk in which f was analytic. So in each disk in which a function is analytic, it has a power series representation. Here's another disk that just barely fits into u from a different center, and again, f's going to have a power series representation there. It's going to be a different power series than the one that I have in the green disk. Nonetheless, I have a representation as a power series. So locally, an analytic function is represented by a power series. Let's look at some examples. So here again, I remind you of the formula. F of z can be written as a power series in the disk where it's analytic, and the ak's can be calculated by taking the kth derivative of f at the center divided by k factorial. Let's start with the function e to the z because its derivatives are really easy to calculate. The kth derivative of f at z is also e to the z, and if we plug in z0 equals 0, then we know the kth derivative of f at z0 is e to the 0, and so that's 1 for all k. So if I wanted to calculate these coefficients ak, the numerators are all going to be 1. So ak is going to be 1 over k factorial, and therefore I find that e to the z is the series of ak, which is 1 over k factorial, times z minus 0 to the k, so z to the k, for all z and c. because the disk of the exponential function, which is analytic in the entire plane, is the disk centered at the origin of radius infinity. So, I can make this disk as large as I want to, and the function is analytic in there, so I might just as well choose the radius infinity. And therefore, this power series representation holds in the entire complex plane. Let's modify things a little bit. Let's look at e to the z just as above, but this time we're going to let z0 be 1. So now the kth derivative of f at z0 is e to the 1, which is e. And therefore the ak's, now all the numerators here are equal to e. So ak is e over k factorial, so that e to the z becomes ak, which is e over k factorial. Z minus z0 minus z0 is 1, so z minus 1 to the k. There would have been another way to see this. Another way to see this would have been to write e to the z as e to the z minus 1, well, that's not true, times e. But e to the z minus 1, I can use the power series representation that I already found. So this is equal to this one e times, and now I use my power series representation that I already found in the first example. I plug in z minus 1 for z right there, so I get the sum k from 0 to infinity. And instead of z, because this is true for all z, I can plug in z minus 1. So z minus 1 to the k divided by k factorial. If I now bring the e inside, I get this representation, e over k factorial times z minus 1 to the power k. Here's another example. This sine function is analytic in the entire complex plane. So if I pick the origin as the center of my disk, again, I can choose a radius infinity here, in which the function is analytic. So f of z is sine z. If I evaluate that at 0 to get the 0th coefficient, I have f of 0 at 0. The first derivative is cosine z. The first derivative at 0 is 1. The second derivative is minus sine z. At 0, that's 0. Third derivative is minus cosine z. At 0, it's minus 1. Fourth derivative, we're back to sine z. Fourth derivative at 0 is 0. And now we're going to keep repeating because these derivatives keep cycling through sine, cosine, minus cosine. And so the numerators of the ak cycle through 0, 1, 0, minus 1, 0, 1, 0, minus 1. And the denominators are these k factorials. So I find a0 is equal to 0 divided by 0 factorial. A1 is equal to 1 over 1 factorial. A2 is equal to 0. A3 is minus 1 divided by 3 factorial. A4 is 0. A5 is going to be 1 over 5 factorial. A6 is 0, and so forth. Altogether, I find sine z is a0, this is 0. This is a1, that's my a2. This is a0. This is a3, a4, a5. So all the even coefficients are actually equal to 0, so I might just well not write those down. I get only odd powers of z, and they have alternating signs, and the denominators keep getting bigger and bigger. They're the factorials of the odd number. So I find z minus z cubed over 3 factorial, that's this term right here, plus z to the 5th over 5 factorial, then minus z to the 7th over 7 factorial, and so forth. If you wanted to write that as one formula, it's the sum of only odd powers of z, so that's why we write the exponent as 2k plus 1. The factorial that I need is the same number, so 2k plus 1 factorial, and the numerator gives me an alternating sign, alternating between plus 1 and minus 1. Now let's look at cosine z. That's also analytic in the entire complex plane, and if I choose the origin as the center of my power series, then again I get a radius of convergence of infinity. We could do the exact same analysis, just find all the derivatives at 0, and then write down the series, or we could remember that cosine z is the derivative of sine z, and a power series within its disk of convergence can be differentiated term by term. I can pull the derivative to the inside of the series, and therefore I find it's the sum minus 1 to the k over 2k plus 1 factorial of the derivative of z to the 2k plus 1. But the derivative of z to the 2k plus 1 is 2k plus 1 times z to the 2k. Now I find myself with 2k plus 1 divided by 2k plus 1 factorial. So what is that? 2k plus 1 divided by 2k plus 1 factorial. 2k plus 1 factorial is 2k plus 1 times 2k times 2k minus 1, and so forth, all the way down to 1. And I noticed that I could cancel out this one factor. And I'm then left with 1 over 2k times 2k minus 1 times 2k minus 2, but that's 2k factorial. So I'm left with minus 1 to the k divided by 2k factorial times z to the 2k. So this time I only have even powers of z, and they alternate in sign again, and again I divide by factorial. So I find 1 minus z squared over 2 factorial, plus z to the 4th over 4 factorial, minus z to the 6th over 6 factorial, and so forth. That is the power series representation of cosine z centered at the origin. So this theorem actually implies that an analytic function is entirely determined in a disk by all of its derivatives at the center of the disk, because the ak's can be calculated by taking the kth derivative of f at the center of the disk divided by k factorial. And the ak is determined by power series. It consists of ak times z minus z0 to the k. The ak is entirely determined. The power series are entirely determined by the kth derivatives of f at the center, and therefore knowing all the derivatives of an analytic function at the center of a disk determines the function. The corollary of that observation is the following. Suppose you have two functions f and g that are both analytic in this disk of radius r centered at some point z0. And suppose you also know that all their derivatives agree at this one point z0. Then the two functions must actually agree by having the same derivatives at one point of all orders. Not just the same first derivatives, but the same derivatives of all orders. If all derivatives agree at z0, then no matter what z you plug in, the functions must agree there. So f and g are actually the exact same function. So that's quite a powerful theorem. In the next lecture, we'll study the Riemann zeta function, its series representation, and the Riemann hypothesis.